Professor Séamus Davis, thanks very much for being with us today. You're a leading authority on quantum physics. You're a professor of quantum physics at UCC. You're professor of physics at Oxford and Cornell also, I believe.
That's correct.
In March, you were awarded the prestigious Buckley Prize in the US, recognizing your groundbreaking work on the quantum microscope. It's an award previously won by 18 Nobel Prize winners, so you're in very impressive company indeed. There's much for us to talk about today. But just before we get into the intriguing and complicated world of quantum, I'd love for our readers and our audience to hear a little bit about your journey to here. I believe, are you originally from West Cork?
Yeah, I'm from Skibbereen in West Cork, born and bred. I went to high school there, De La Salle, and there was a great physics and math teacher there, an Institute of Physics Prize winning teacher. And I learned my physics and math and my love of those subjects from him. Liam Donovan is his name, and I met him 2 weeks ago. He's still hale and hearty, so he's a great guy. And from there I went to UCC, and they had a fantastic physics program in the early 1980s. It was both superb and notorious at the same time because it was extremely difficult. But many physicists distinguished on the world stage were educated in that program. And from there I went to Berkeley as a graduate student to do my PhD, and I did a fairly good job, and after a while they hired me as a professor, so I stayed in Berkeley for about 20 years, 10 as a professor and 10 previous to that. Then moved to Cornell for about 20 years. Then I wanted to come home, so UCC and Oxford very generously, with a great deal of help from SFI, arranged for a joint appointment. And it's a very interesting joint appointment. I don't have two research groups. I have one research group, and the members who work in Cork spend much of their time working in Oxford, and the members in Oxford spend their time working in Cork. So it really is an international research group, and that's been great fun. That's how I got here.
Tell me a little bit about today, and before we get into your actual research,
Yeah.
I'd love to just get your take a little bit on quantum and, you know, how you would describe quantum. I know this is a very big question.
Yeah, right.
And I suppose most interestingly, the potential for quantum and how it could change how we do everything.
Right. So there's many, many things one could say about that. So first of all, you know, what is quantum? Question, what is quantum? That's like saying, what is God? There is no answer to that question. You could say, what is quantum theory? Quantum theory now is a 100-year-old theory. The centenary will be in 3 years, I think. And it's the best theory of fundamental physics ever achieved. It's a pinnacle achievement of the human race. And although none of us realize it, much of our civilization depends on our control of quantum mechanics. Already, it's critically important. So that's kind of the background of quantum mechanics. Now, what a lot of people are talking about now when they say quantum is quantum technology, right? Quantum technology is only coming into the frame now. It's only just beginning to grow rapidly now, making new devices that use the special properties of quantum mechanics to do things better and faster than they could ever have been done before. But there's a classic case that many of us know about where quantum technology has already been working for 20 or 30 years, which is MRI. Magnetic resonance imaging is a purely quantum mechanical process. The whole thing is quantum mechanical, and it works beautifully, of course. And then finally, quantum computing. The great focus is on quantum computing because, at least on paper, quantum computing will render semiconductor-based classical computing. It may not make it obsolete, but for the really superpower tasks, quantum computing can already do better than it, and it's only in its first few years. So all these huge corporations are investing hundreds of billions of euros in the race to build economically viable quantum computers, and there are already some on the market.
And I mean, how far away are we from, in your view, from it being accessible to, you know, the multitudes?
Right. So quantum computing has already been accessible to scientists for about 5 years. And in the last 2 years, something like a dozen major physics discoveries have been made by using quantum computers. So in terms of functionality, they already exist. And if you had 15 million euros, you can buy one and put it in your home. That's about how much they cost. Now, the reason why we can use silicon-based devices is that they're cheap, they're mass-produced, and they work at room temperature. Whereas more or less all commercial quantum computers at the moment operate at ultra-low temperature. So one of the things we work on very hard, and the commercial computers are superconducting quantum computers. So to make them work at room temperature, we need a room temperature superconductor. So in the quantum materials community, there's a race all over the world to make room temperature superconductivity, so we could make room temperature quantum computers. If we could achieve that target, then we would end up with superconducting iPads, I don't know, 10, 20 years from now.
10 or 20 years, you think?
If you start your clock on the day when you have a room temperature superconductor, it won't be long.
Yeah, incredible to think, because the temperature...
It's just the cryogenics which is limiting it now. It isn't the quantum computing. The quantum computing works.
And I mean, do you see a space where you could almost have quantum computing as a service where you have access through software?
Yeah, so I'm old enough to remember when classical computing was a service, big giant IBM computers. There was just a few in Ireland. There was one in UCC when I was going to college. But those days pass away very fast. The rate of innovation is so fast now that if we had the right quantum materials, we probably would end up with quantum laptops in a short time.
Okay. Fascinating to think it could be as soon as that.
It didn't take long to get from Casio watches and calculators to where we are now. So we could do this. We will do the same thing again with quantum technology.
Incredible to think of it. And I mean, it could change literally how we research the environment, how we look at health.
So there are many problems which are provably not solvable by using a classical computer. Within the life of the sun or something, you can't, for example, predicting the climate accurately in the future. It's completely impossible now. But if quantum computers are said to be billions of times faster, problems like that would come within the range of tractability. Or designing new biomolecules, new proteins, for example, for health. You can't do that with a classical computer, but you could with a quantum computer. Discovering new materials, same thing. So on paper, there are fantastic opportunities.
And in that context, tell us a little bit. I mean, the Buckley Prize was partly awarded for your work on the microscope in the basement in Cork. So tell us about this basement in Cork.
The semiconductors in our present computers, telephones, iPads, and so on, they were discovered in 1833 by Michael Faraday. The fact that they had electrons in them wasn't discovered by Thomson until 1898. The fact that the electrons were quantum mechanical wasn't discovered until the early 1930s by Bloch and his colleagues. And the fact that you could make devices wasn't discovered until the early 1950s by Shockley and Bardeen and so on. So in order to get these wonderful devices, it actually took almost 150 years of fundamental research, right? Now, if we want to have quantum technology in the future, we have to have macroscopic quantum materials which have the properties which are necessary for that technology to work. So right now, there's a race all over the world in the study of quantum materials of different types. We're looking for high-temperature superconductors. We're looking for special topological insulators. We're looking for monopole materials, all kinds of exotic materials. Okay, so now you're searching for new quantum materials of a type which have no precedent. So how would you know, right? Suppose I said, well, that looks like a topological superconductor to me. Well, how would you know? We have no way of knowing. So the other side of the coin is we have to invent the instruments which allow us to interrogate the physics to determine the state of the material. And we do a lot of that, developing specialized new quantum instruments which, given a new material, we can visualize the quantum mechanical electronic structure at the atomic scale, and sometimes we can diagnose within a day how these materials work. So the development of these very exotic quantum microscopes is a piece of the jigsaw of developing quantum materials, which is a piece of the jigsaw of developing quantum technology. That's how it fits together.
And it's kind of amazing that we have this here in Ireland, down in UCC. They're
Amazing to me.
It's not amazing to you, but am I right that there's only 6 in the world?
There's only a few machines of this type in the world. Two of these types of machines, were developed by my research teams over the last years. That's what the Buckley Prize was for.
But it's wonderful to have that
It's
coming
fabulous.
out of
You
Ireland.
should see the students. They have a wonderful...
I can imagine. I'll have to come and visit actually sometime. I'd love to see it. Tell me a little bit more then about the team and how it works across internationally. I'd love to hear a little bit more just about the people who are working on it as well.
So again, in the context of exploring these very exotic materials, there are few, if any, commercial instruments which can do the necessary experiments. But, even in Oxford or even in Cornell, you still don't have a complete suite of instruments. So at least in our own research program, which is a fairly big one, we have a large number of international collaborators, senior scientist collaborators. We have different specialized instruments in the different labs. And when a certain research campaign is going on, the student from one lab will go to each of the other labs as necessary to carry out the relevant experiments. And, well, it was a bit of a guess, to a bet that would work. But now we know it does work. In the modern world, there's no difficulty with that.
Incredible. And, again, as you say, it's no big deal to you because it's what you do. It's your job, exactly. But tell me a bit about Ireland on the global stage. I mean, we're a small country at the edge of Europe. It is quite remarkable. Do we punch above our weight in quantum?
Well, does Ireland punch above its weight in rugby?
Definitely.
How about politics?
Yes.
Yes, right. So how about literature and art?
Oh, definitely.
Okay, so why not science?
Exactly.
Yeah.
I couldn't agree more.
Yeah,
I couldn't
don't
agree
see
more.
any reason why we can't achieve at the same level in science.
Yeah, and we have a little bit of a heritage, don't we?
We have the attitude as well.
I like that. But so, I mean, do you think that there's a lot going on? Like I'm trying to think. There's the new MSc in quantum in Trinity. UCC. So you have. Do you feel we're trying? We're doing enough?
Yeah, things are accelerating very fast. That's great. We have fabulous students. We have capability to recruit up from all over the world. I was relieved to discover that we have people from all over the world in our labs in Cork. We have tremendous support from SFI. And we have a good reputation abroad. So at the level of fundamental physics research, I think we can be world class. We could be in the top 10 in the world. I don't see any reason why not. There are other small countries in Europe which are very famous for their fundamental research. So I wouldn't think that's a problem. Now, in terms of growing that out and developing a big enough industry in Ireland to hire some fraction of 1 million people, which is what everyone wants from quantum, right? But that involves the companies. So we have some of the world's greatest technology companies, many of them with their European headquarters in Ireland. But most of the work they do here is, if they do research, it's research into semiconductor photonics. Virtually none of the quantum research in IBM or Google or Rigetti or any of those companies is in Ireland. So we do have a little bit of a kind of a barrier to convince those companies that they would benefit by having some of their major flagship quantum labs in Ireland. But if we could convince them, I'm sure they would benefit and they would stay. History shows that they would stay.
And I presume, what would help that is the growth and scale in the area as well. So,
it's like all things. It's they have to grow together, right? If you overgrow the skills, and there's no jobs for them, then all those Irish students will leave, and that's exactly what we don't want. And I should say, it appears to me now like we are not educating enough people to become quantum physicists, quantum chemists, quantum engineers, quantum software people, etc. for the future in Ireland. And what's going to happen is Ireland's probably going to have to recruit a lot of people from abroad, roughly, I guess, 15 years from now.
Yeah.
Which I would think is a mistake. It's not necessary, but it's because we're not educating fast enough now.
Yeah, it would be a pity not to do both, wouldn't it? It's great getting the international people in, but you'd hope there might be a little bit of osmosis as well because of some of the incredible international people coming here?
Anyway, I think in the world of quantum technology, quantum computing, and its future economic impact, Ireland could be a world leader. It has all the same advantages it has in other industries.
I want to ask you a little bit more about yourself as well. So you mentioned your teacher already. You could name him again for me.
Liam Donovan.
Yeah, because it's lovely to name check these people, I think. But have there been other sort of inspirational figures in your life that, you know, you went, okay, I really want to do this?
Yeah, so when I went to Berkeley, I had learned a lot about quantum mechanics in UCC, a tremendous amount, more than I even wanted, actually. But anyway, when I went to Berkeley, I got a chance to work on macroscopic quantum mechanics, something which, the way education works, people are taught in high school and in college that quantum mechanics is a theory of things which are incredibly small. Okay, that's complete fake news. That's just nonsense. There's no rule of nature that says you can't have an object of this size be quantum mechanical. So in graduate school, I was working for Professor Richard Packard, who's a very famous macroscopic quantum physicist, and I just discovered all of the amazing things which we already know can happen due to quantum mechanics in the macroscopic world. And I realized there's really no reason why we can't have a fully quantum mechanical technological basis set. There's no reason why not. And it's certainly not true that quantum mechanics is always hidden from us at the atomic scale. So that had a huge effect on me. I always, since that time, I really kept my attention on macroscopic quantum physics.
Amazing. The role models are so important, aren't they, as well? I mean, people who are really getting into the... So I would imagine you must be a great influence on people down in UCC as well.
Well, yeah, especially in the world of fundamental frontier research. It's very different. You know, you can be a brilliant student and learn everything in the book and ace all your exams. But that doesn't necessarily mean that you would have the capability to make a fundamental discovery. They're almost orthogonal skills. It's like learning how to sail a boat, right? Learn how to sail a boat from a book, pass all the exams, okay? And then take a sailboat out off the West Coast in December, and you'll find out you don't know anything about sailing a boat. So teaching people how to, they need courage, they need curiosity, they need dedication, they need a lot of other characteristics besides the capabilities to solve equations, to put in the years necessary. And they have to be confident in themselves to put in the years necessary to make fundamental discoveries. So, you know, aside from doing research and writing papers, a lot of my effort goes into teaching people how to do that.
Yeah, and it's a privilege for them to have you there in UCC, it is, you know. And I mean, there must be so many, and I'm sure the Buckley Prize was one of them, but I mean, if you could pick out one or more career highlights over the years.
So when I was an assistant professor at Berkeley, there had been a prediction which had been around for around 35 or 40 years, that there's a macroscopic quantum phenomenon where you would have a fully quantum mechanical fluid. You apply some pressure to it, you do something, other special stuff, but then it should spontaneously generate a coherent quantum mechanical sound called Josephson sound. And I had been searching for that for about 15 years. It was a long haul searching for, but it's a deeply fundamental effect. Lots of people were focusing on this. So we had built a very elaborate ultra-low temperature, ultra-low vibration experiment to listen for this incredibly weak quantum mechanical sound, and failed and failed and failed, could never hear it. And so one Saturday morning, we had failed again. And my postdoc and I were in the lab, Sergei Pereverzev is his name, and we just said, this thing is not working. So why don't we take the output of our electronics, and instead of looking at it on the computer screen, we put it on the earphones and listen to what's happening inside the experiment, okay? So he put on the earphones first, and he listened, and he almost fainted. And then he gave them to me, and I listened. And the quantum mechanical sound was there all the time, okay? The human brain can pick out a sound inside the noise, which is so tiny that you never see it on a computer screen or on an oscilloscope. But to the human brain, that's how you can hear something in an orchestra. So we discovered this very famous result, somewhat serendipitously, by trying to diagnose the machine by listening to it.
Wow.
That had a big effect on my career because I got tenure at Berkeley.
Yeah. They were very good headphones, very important set of headphones. And I suppose for young aspiring scientists, physicists, the whole, who have a kind of even a vague idea of getting into the whole area of quantum. I mean, would you have advice for them?
Although we don't know which one of the great companies or which subset of the great companies will turn out to be the quantum company of the 21st century, some of them will. Without doubt, there isn't the slightest doubt that there's an enormous number of potential applications for quantum sensing, quantum communication, quantum cryptography, quantum computing, quantum software writing. So it seems perfectly clear that for highly educated physicists, mathematicians, and engineers and so on, there'll be fabulous quantum careers in the future. Now, if you ask me which ones they will be, I don't know. Nobody knows, right? And if you had asked someone in 1965, which job will I have programming the iPhone? Well, of course, you can't answer that question. So, but in terms of the opportunity, it appears like there will be a very wide range of very satisfying and important positions available in quantum technology in Ireland and Europe and throughout the world.
And just in that context, do you have any visibility of the work that is going on in some of these companies and how impressive it is?
Yes, I mean, they're accelerating very fast. Yeah. So now we're talking about economics here. It's important to understand that the various quantum mechanical procedures which are used on a qubit, a quantum mechanical bit, they have been understood since the 1940s. To the physicists, there's nothing new about them. To the engineers, they're amazed, but to the physicists, the Nobel Prizes have already been given their solved problems, right? But which actual device, which platform those procedures will be carried out on is a race. And it's mostly an economic race now. Superconducting quantum computing companies like Google and IBM and Rigetti are racing ion trap quantum computing companies like IonQ. And they're racing cold atom companies. And they're racing, quantum dot companies. Nobody knows who's going to win that technological race. Whoever can get a device which is cheap that's economics. Whoever can get a device which is cheap to produce and works at room temperature and is functional as a quantum computer, they will win. So my own energy is going into finding high temperature superconductors, because I think that if we had room temperature superconductivity, then the superconducting quantum computer people would win. But, that's a partisan point of view.
I love it. And just again, for people, who are coming across you sort of for the first time or whatever, is there something that might surprise them about you? Anything that we don't know about you that might surprise them? We ask everybody this.
I don't know about surprising them, but my hobbies are bicycling whenever possible, so that wouldn't surprise anybody. Although bicycling in West Cork is a challenging endeavor. I've crashed several times. And then my other hobby is classical history and literature. If I hadn't been a physicist, I hoped to be a literati or a historian or something. But there's only time enough for one career, so the second one is my hobby.
Yeah.
And it's one thing is very, very interesting about being at Oxford. We haven't said much about Oxford. In the colleges in Oxford, you're not segregated by discipline. So when you sit down to have a meeting or to have lunch or something, the people around you aren't physicists. They're often economists and philosophers and historians. And that milieu is actually it's wonderful, because you get to talk to people you normally would never talk to about things you would normally never get to talk about. And I enjoy that very much.
That's actually very healthy, because, and you were talking about it there earlier, but that interdisciplinarity idea that, of course, you're talking about economics here. You're not just talking about engineering or physics or technology or...
When I was doing that podcast recently, one of the things we discussed is that in Ireland, it'd be good to have a forum where the different groups of people had some public forum where they could communicate with each other, where the artists and the literati and the historians and the philosophers and the scientists actually could get together once a year and talk to each other. It would be a very useful thing for society.
I really like the idea. We should really look into that. That's it's funny, because recently I did a panel for the Goethe Institute on quantum and the arts. And like, it is fascinating what,
And everyone can benefit.
Yeah,
when
exactly.
You're in the frontier area, not all new ideas, including my own, are good ideas. but it's always better to have more new ideas than less. So the more people we can get together to work on these problems, the faster we'll make progress.
To finish, in a way, I suppose your own, and you've discussed many of them, but your own kind of aspirations for how we could change the world with quantum.
Okay, it's important to have an honest discussion about that. So it's true that the potential for especially quantum computing is deeply impressive. We can use it to solve logistical problems. We could use it to stabilize, in principle, we could stabilize the economy because we could see farther into the future with that type of computing power. We could use it to improve our understanding and eventually control over the environment. We could use it to understand the human body a bit better. We could use it to understand the human mind. There's a vast number of wonderful things that you can state where computing power, let's say, which is 1 billion times faster, would allow us to do amazing things, no doubt about it. But the truth is that everything that human beings invent can be used for good as well as for bad, right? So we have to be careful. And we're all having this discussion about AI right now.
Yes.
We have to be careful. Quantum computing is not guaranteed to be good. It's only guaranteed to be good if we keep control of it, right? And that's a place where we need to put more attention as it develops, I think. Because there is, for example, quantum computers, one reason why national security people pursue quantum computers is that, in principle, you can use quantum computers to crack the RSA encryption code that we use for our data storage and commerce. All of our commerce is under RSA 64-bit now. But quantum computers could crack that encryption and break into your bank account. So it's something we all have to consider very carefully. But at the moment, it appears like the promised benefits greatly exceed the dangers. So I think we should move on.
Okay, very good, very good. Listen, it's been an absolute joy to talk to you today, and really looking forward to seeing what happens in the next 10 to 20 years in this area.
Yeah, there's no way to predict the future, especially in a circumstance like this. And you know, the truth is, although there are hundreds of perfectly genuine, dedicated companies working as hard as they possibly can to crack technical problems to make quantum computing, there are also quantum investment scams out there. People asking you for your money for their latest quantum idea. If you actually mine down into the idea, you find out it's nonsense. But the people, you know, with the billions don't always know how to solve the quantum mechanical equation. So there is a good deal of hype as well, and we have to be careful about that.
Yeah, no, that makes a lot of sense. Thanks so much for taking the time to be with us.